Hello, my name is Dr. Rohan Sharma. I shall present here a series of lectures on the sorting networks. We have initially we know that the algorithms like the bubble sort, merge sort, quick sort are primarily being designed for the sequential architecture. Here, our aim is that in this particular video and the subsequent videos, we want to design the algorithms for the parallel architectures. Now, the different type of parallel architectures, what are they, and what are the characteristics? We shall discuss them into next few slides. For example, in this particular slide, there there is a four-node linear array. There is a four-node linear array. All of you have studied about it into the graph theory, in which the last two nodes are having the degree 1, while the intermediate nodes are having the degree 2. So, uh, so the nodes can be arranged into a linear array architecture. Or if the last two nodes which are having the degree 1 are to be connected to each other, then it will become a ring or a cycle, or it is also being known as a one-dimensional torus. One-dimensional torus, so it is a linear array, it is a ring or one-dimensional torus. In the same way, in the same way, it is a two-dimensional mesh. It is another type of topology. Rather than having the one-dimensional topology, it is a two-dimensional topology having the 16 different nodes, in which in which each of the intermediate nodes is having the degree 4, and and the and while the nodes are at the periphery are having the degree 2 or 3. Here in this figure, it is shown that it is the part of some other figure. So it is being shown that ideally each of the nodes are having the degree 4. But into the actual cases, into the actual cases, the last nodes which are at the periphery would be either having the degree 2 or the degree 3, while the intermediate nodes are having the degree 4. Now, if we will connect the last two nodes with each other, for example, if these two nodes are being connected to this node, and this node is being connected with this node, and this node will be connected with this node, then we shall be able to get a structure like this. This is a two-dimensional torus or a two-dimensional mesh with the wraparound links. A two-dimensional mesh with the wraparound links. Here in this case, here in this case, you can be able to observe that these particular edges, 1, 2, 3, and 4, fourth edge, and the 5, 6, 7, and 8 edges. These 8 edges are extra in comparison to this particular topology of the two-dimensional mesh, such such that this two-dimensional uh, such that these edges are being known as the wraparound edges or the wraparound links. So this is a two-dimensional mesh with the wraparound links, or it is also being known as the two-dimensional torus. This same type of architecture can be also be extended into a three-dimensional mesh, four-dimensional mesh, and third-dimensional mesh, and and so on. So this three-dimensional mesh is having the three nodes. It's having the total 27 nodes. Similarly, similarly, there are some other type of topologies like the hypercubes. For example, it is a two-dimensional hypercube which is having the four different nodes. Which is having the four different nodes. Now, if we will combine two different instances of the two-dimensional hypercube, then we can be able to get a three-dimensional hypercube. If we will connect the elements on one-to-one basis with in between the nodes of a two-dimensional hypercube, such that in order to such that these four nodes are the part of the one of the hypercube, and these four nodes are the part of the next hypercube. And in order to distinguish in between them these four nodes with other four nodes, the zero is being prefixed towards the first instance, and the one is being prefixed towards the second instance of the hypercube, such that this this eight node structure is being derived from this two-dimensional hypercube. Similarly, there is also a one-dimensional hypercube. The one-dimensional hypercube is being obtained by combining two different one-dimensional hypercubes. And again, in order to differentiate in between them, the zero is being prefixed with respect to the first one-dimensional hypercube, and one is being prefixed toward the second one-dimensional hypercube, such that when we will combine establish an edge in between the nodes of the one-dimensional hypercube, then we will get a two-dimensional hypercube. Similarly, we can be able to get a four-dimensional hypercube by combining two copies of the three-dimensional hypercube, such that it is the first copy, and it is the second copy. And in order to distinguish in between these two copies of the hypercube, the zero is being prefixed towards the one of the node towards the each of the node of the first hypercube. Similarly, into the second hypercube, one is being prefixed with respect to the second hypercube, and and then and then and then an edge is being established in between uh, one of the node of the first hypercube and one of the node of the second hypercube. In this way, this 16 node architecture would be obtained. Now, in the same way, we can be also be able to design this five-dimensional hypercube. Now, the now this four-dimensional hypercube has the biggest characteristics, has an interesting characteristics, that it is having only two nodes in each of the dimension. In each of the dimension, for example, this node is having one node into this particular dimension, and there's no other node into the other dimension, into this dimension. So it has another neighbor into the other dimension. Similarly, this node has one of the neighbor into this dimension, then another neighbor into the other dimension, then another neighbor into the other dimension. So so these edges, first, second, third, and the fourth edge, similarly fifth, sixth, seventh, and the eighth edge uh, are connecting this hypercube to the other hypercube into the fourth dimension. So that is why it is being known as the four-dimensional hypercube. Now with this brief introduction about the topologies, now we should discuss about the sorting. That what that that what is sorting and why is it important? The sorting is important for the parallel computing, because if we are running the processes or the programs onto each of the nodes of the underlying topologies, then we can be easily be able to transfer the data or route the data among their processes. So 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 this particular linear array will be running the same algorithm on each of the four nodes, that the algorithm will be running on this node, and this node, and the data has been transferred from the first node to the other node with respect to the sorting of the data on these four nodes. Similarly, if the data is in the sorted order onto this ring, then we can easily be able to transfer the data in between these nodes. With but the condition is that the same piece of code for the sorting is running or executing simultaneously into each of the four nodes of this ring. Similarly, the same code or algorithm is being running onto this particular set of nodes. Similarly, with respect to these three architectures that we have discussed earlier, that it is a two-dimensional mesh, it is a two-dimensional torus, and it is a three-dimensional mesh. With respect to this first architecture, thus for these 16 nodes, the 16 copies of the algorithms are running onto these 16 different nodes. Similarly, these similarly 16 copies of the processes are running onto these particular nodes. Now, whenever these algorithms are executing simultaneously onto each of the nodes of a particular topology, then if the data is into the sorted order, then we can easily be able to transfer the data or exchange the data in between these machines. The same case is about the hypercubes, that that with respect to this two-dimensional hypercube, four copies of the same algorithms will run simultaneously on this two-dimensional hypercube. Similarly, the eight copies of the same algorithm will run onto these eight nodes simultaneously, and they will exchange the data. And if the data is into the sorted order, we can easily be able to exchange the data. Now the same case is with respect to the four-dimensional hypercube. Now there are different two types of sorting. The first is the internal sorting. If suppose we have some data, suppose we have some data in which the memory is limited, and and also we have to just sort a list of around 16 different elements, and for which all of the data can be sorted into the program's process main memory or the RAM. Then this type of sorting is being known as the internal sorting. But if suppose that we want to sort 100 million set of numbers, and those 100 million set of numbers or alphabets or any other data can be allocated. All of the data cannot be able to cannot be assigned to the main memory simultaneously, and hence some of the data are to be stored into some auxiliary storage like the hard disk drive, or to the flash drive, or to the magnetic tapes which are being used around 25 years ago. So here they have to be stored into some hard disk drive. So this type of sorting in which we need some extra memory it will be known as the external sorting. So the examples of this type of sorting of the internal sorting is that bubble sort, insertion sort, quick sort, merge sort. These are the examples of the internal sorting. With respect to the external sorting, the examples are the distribution sort. The distribution sort it resembles with the quick sort. The other thing is about the external merge sort. The external merge sort is based upon the merging process, of the merge sort, and then divide their values. Now, after discussing the types of the sorting, now we shall discuss about the different types of algorithms. Now, there are two different types of algorithms are there. First is comparison based, and the other thing is about the non-comparison based algorithms are there. Now with respect to the comparison based algorithms, now with respect to this comparison based, that suppose that we want to suppose that we want to sort the data into the ascending order or into the descending order. So with respect to this sorting of the data into the ascending or descending order, if we are simply comparing two different elements by their numerical value, and we are not considering any other property, then it is the comparison based sorting. And the other type of sorting is non-comparison based, in which we are comparing two different elements with respect to some predefined notion. Either that notion can be some binary representation, that if the binary representation is of this form, then we can be able to compare, or some other properties, or some other property. So if those properties are being satisfied, then only we can be able to compare two different elements. So the example of the it is being observed that the lower bound or the computational complexity for the sequential algorithms has the lower bound as the theta of n log n, which is being observed for the examples of such networks, such algorithms like the insertion sort, like the merge sorts. like the merge sort, where the complexity is theta of n log n. Similarly, with respect to the heap sort, it is also having the complexity as theta of n log n. With respect to the non-comparison based, it has been observed that the lower bound complexity of these algorithms is theta of n.